Pluto, the confusing peewee planet living at the outside extents of our close-by-planet bunch, is stirring up energy inside the infinite local area. Progressing reports demonstrate an expected encounter with Neptune, raising concerns among analysts and space fans alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this divine clash. But how did Pluto end up on a collision course with its distant neighbor? And what could this boundless crash mean for us here on Earth? Let us explore this unfolding event. Once remembered to be an irrefutable planet, Pluto was consequently renamed as a minor planet because of its interesting circle. Despite this change, it continues to delight and connect with space specialists. Progressing forecasts from noticeable experts highlight a pushing proximity between Pluto's circle and that of Neptune. These experts caution against a potential collision between the two planets, representing a critical danger to Earth. Pluto's excursion around the Sun is marked by its unique attributes. Within our close-by-planet group, its circle ranges an amazing 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution, adding to its intrigue. The astoundingly roundabout shape of its circle is a departure from the almost round orbits of the major planets. Besides, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its path more extreme compared to other planets. One conspicuous feature of Pluto's orbit is its crossing point with Neptune's path for about 20 years in each orbit. Pluto ventures closer to the Sun than Neptune, defying assumptions based on their relative positions in the planetary system. So why hasn't a collision happened between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The examination of Pluto's orbit began shortly after its discovery, presenting a surprising challenge for cosmologists. Unlike most planets, whose orbits align relatively close to the ecliptic plane, Pluto's unique features include a steep inclination and an erratic orbit. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these complexities serves as proof of the intricacies inherent in space mechanics. The three-body problem in space involves calculating the motion and gravitational interactions among three celestial bodies, like Pluto, Neptune, and the Sun. This problem explains the complex exchange of their paths and gravitational forces. Terms like AIML, libration, and the Koi influence help explain this heavenly mystery. Astrophysicists argue that a libration, responsible for maintaining planets in their orbits, plays a critical role in the Pluto-Neptune system. This term refers to the fact that when Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune, essentially preventing potential collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it is arranged predominantly above their orbital plane, offering an additional layer of protection against impacts. The Koi influence explains why Pluto's orbit around the Sun appears irregular but remains stable over time. Despite apparent irregularities in space, numerical simulations in the late 1980s revealed that, despite its consistent properties, Pluto's orbit is, in fact, chaotic, with slight initial deviations leading to significant changes over long periods. However, Pluto's unique orbit maintains stability over incredibly long timescales, keeping disorder within limits. Progressing computer models have enhanced our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path near the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, contributes to the stability of Pluto's orbit. Furthermore, Jupiter's massive gravity exerts a significant influence, while Saturn's impact, though smaller, also plays a role. Through extensive studies, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the protected and stable motion of Pluto in space for billions of years. These phenomena are part of what keeps the control and consistency of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater turmoil, potentially leading to collisions or ejections from stable orbits, with far-reaching consequences for other celestial bodies. Understanding Pluto's orbit is especially important in discussions about a possible collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can reach equilibrium through the complex interaction of gravitational forces and orbital mechanics. Constant observation and analysis of these phenomena are vital for gaining a better grasp of our place in the universe. Investigating the depths of space often uncovers the unpredictable nature of celestial bodies. Moreover, Pluto's orbit serves as a perfect example of this erraticism. The nature of orbital chaos strikingly demonstrates the delicate reliance of a celestial body's path on its initial conditions. As exemplified in Pluto's case, even slight variations in the dwarf planet's position or speed can drastically alter its long-term orbit. Automatic simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, space specialists can observe how even minor changes can have a significant impact on Pluto's trajectory. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's orbit. Despite factors like AIML and libration contributing to its stability, Pluto's orbit can still show inconsistencies. Even a slight initial difference in Pluto's position or speed can lead to significant changes in its orbit over many years. Nevertheless, despite this intrinsic chaos, Pluto's orbit remains stable for such extended periods, crossing billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized order, anticipating celestial events. Predicting the future movements of celestial bodies, especially with planets like Pluto that have unusual orbits, is extremely difficult. The inherent unpredictability of these systems makes long-term predictions uncertain. Numerical simulations help us understand and estimate future movements of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily depend on precise initial conditions and simulate complex interactions. Even a small error can lead to vastly different results, making accurate predictions challenging. The turbulent nature of celestial orbits, like Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Grasping the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary system. It shows how the presence and position of each planet can affect the stability and direction of other bodies within the system. Despite these unpredictable forces, Pluto's orbit remains remarkably stable, and understanding these forces is crucial for future exploration and study. Astrophysicists are communicating concerns about a likely effect between Pluto and Neptune. Neil deGrasse Tyson, an eminent astrophysicist, offers a novel viewpoint on the secrets of our nearby planet group, especially in regards to Pluto. Tyson, popular for renaming Pluto as a bantam planet rather than an undeniable planet, shares canny considerations on how we might interpret heavenly mechanics, which is continually advancing. Tyson sees Pluto's renaming not as a minimization, but rather as an essential change in accordance with our developing information about the different objects circling the Sun. His way to deal with heavenly mechanics includes consistent learning and adaptation. He sees the intricacies of orbits like Pluto's as a reminder of how much more there is to find in space. Tyson trusts that the appeal of these secrets makes space science so interesting. Furthermore, Tyson knows how space-related events and revelations catch the public's attention. He witnesses events like Pluto's renaming and its unique orbit as amazing opportunities to connect with the public's imagination and interest in the universe. By examining the dynamic and, sometimes, the chaotic parts of celestial mechanics, Tyson fosters a deeper understanding and excitement for the universe. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and secrets of the universe. Working alongside other analysts, Tyson actively warns the public about the potential dangers of Pluto's surprising orbit. After broad investigation of Pluto, he has raised concerns that the three-body issue could pose a serious threat, proposing that an impact with Neptune might be extremely overdue. Moreover, Tyson stresses how such a crash could disturb the equilibrium of the universe and lead to unfortunate outcomes, stretching even to Earth. An impact between Pluto and Neptune would be an unusual and devastating event in our solar system. This crash would release a gigantic amount of energy, likely deteriorating Pluto due to its smaller size and cold composition. Debris from the impact could spread throughout the planetary system, presenting potential threats to other planets and their moons. For Neptune, such an effect could possibly alter its atmosphere and orbit, depending on the specific details of the crash. Michio Kaku, a well-known theoretical physicist known for his work in string theory and science communication, offers an interesting viewpoint on this situation. His perspectives on the future of space exploration and the connection between celestial mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto, as indicated by Kaku, can offer critical insights for future space missions. This knowledge can help navigate the solar system more effectively, anticipating potential hazards and planning missions to the outer reaches of our solar system and beyond. Kaku stresses that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, offering a framework for approaching and understanding distant worlds. In examining the physics of planets, Kaku frequently highlights the significant connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are connected to fundamental principles of physics. Kaku's work in theoretical physics, especially in string theory, aims to grasp these principles at the most fundamental level. He suggests that considering the intricacies of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential impact, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in space science, providing a unique observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the key forces and matter in the universe. The impact of such an event in the planetary system could generate extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme conditions. A critical focus in string theory is the gravitational waves produced by the impact, which could provide valuable data for testing string theory predictions related to gravity and spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a significant example of celestial mechanics, demonstrating both stability and chaos within our solar system. The unusual features of its orbit, influenced by the gravitational forces of nearby planets, particularly Neptune, highlight the complex and dynamic nature of space. The universe holds many secrets, and the three-body problem is just one of them. There are other potential calamities that researchers anticipate. While the chances of planets colliding in space are very low, it is not entirely impossible. The way planets' orbits are affected by other factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1 with 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary orbits less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently happening. Scientists closely monitor these systems to understand how planets influence each other's orbits, particularly when they are near one another. This information helps us understand planetary movement in space. Rogue planets, floating through space without orbiting a star, present an additional curious phenomenon. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events. For example, the close approach of another star or dynamic instability in other systems can cause these rogue planets to travel vast distances, potentially reaching areas far from their origin. During their solitary journey, there is a possibility of them encountering another star system. If one of these rogue planets enters a nearby planetary system, there is a slight chance of a collision with a planet in that system. However, given the vast and generally empty nature of space, the likelihood of a rogue planet directly impacting another planet is incredibly low. The vastness of interstellar distances and the scarcity of planets in open space act as barriers against regular collisions. Moreover, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters even more improbable.